having our second keynote speaker, Professor Divyakant Agrawal from UC Santa Barbara. Divy does not need a lot of introduction. Divy has been our well-respected researcher in our community, and Divy's work has been on many different subjects in the data field, or database field. To name a few, parallel database systems, distributed database systems, transaction processing, and cloud computing, and security. And Divy also has a very impressive record of producing good students. To name a few recent ones, Professor Aaron Elmore at the University of Chicago, and one of my colleagues, Professor Faisal Nawab at UC Irvine, they're all the result of Divy's education record. Today, Divy also received many awards. Just to name a few, he's IEEE Fellow, ACM Fellow, and Divy is also the chair of our ACM SIGMOD. Without further ado, let's welcome Divy.
I have to get my devices in order. All right, I want to thank Chen Li for that generous introduction. And as you all know, the credit is not all mine. I think a lot of the credit goes to my colleague, Amra Labadi, in training the students. I'm not I take the second seat when it comes to students. Anyway, I want to, first of all, I'm extremely honored and at the same time humbled by the invitation for the keynote. I'm not a keynote material. I mean, I think when I see the reviews that come from the database peer reviewers, I often think that I have to go back and learn how to do research. So anyway, I want to thank the leadership team for ICDE for extending this invitation and having a trust in doing a talk as a keynote. All right, so the title of my presentation is Trust in the Untrusted World, which is sort of provocative and at the same time is a bit ambiguous. So I'm going to start with a couple of disclaimers so that the record is set straight, especially since I see Mohan is sitting here. So the first I want to say is that I am not addressing the issue of trust and mistrust in the context of the physical world. What I'm going to be doing is sort of narrowing that scope to the things that I know about, and in particular, I'm going to be talking about the issue of trust and malicious activity in the context of our digital infrastructures, computing, and networking. The second disclaimer I have is I do not have an overarching solution to this problem. What I'm going to do is I'm going to give you point solutions of how to deal with kind of untrusted infrastructure in the context of a few applications. And what's my intent is to just make us all aware of what we need to be able to do in order to accomplish, or overcome malicious activities in such environments. So that's kind of is my intent. I'm pretty sure that after I've presented some of these point solutions, you're going to be extremely dissatisfied as to what I have to offer. And that's exactly the intent of the keynote is you go back and think about these problems and perhaps come up with better solutions. I just want to mention this work is based on the PhD thesis of one of our students, Ishtiaq Ahmed, who has done all the heavy lifting, and we are the one who take the glory. So that's me and my colleagues, Amra Labadi, and a junior colleague, Trinab Gupta. Okay, so let's start, a quick motivation. I don't really need to make it very long. Basically, what has happened over the past 2 decades is that our lives have, there is a large part of our existence has moved to the virtual world. And this existence has 2 issues. One, it is we are highly interconnected. We rely on many services and applications to provide our services. And more importantly, we are also become interdependent on each other by, all the communication mechanisms that are used among individuals. The consequence of these interconnections and dependencies is that there are myriad of factors that are involved in providing us these services, and you cannot always rely on the trustworthiness of these actors or these agents that are involved. Okay, I do want to acknowledge that over the last 50 years or so, we collectively, this community as well as our other sister communities have indeed transformed the world for a large number of users, billions of users. For example, if you go to India, the amount of access to information and resources any ordinary individual has is mind-boggling, right? So we have vast amount of information at our fingertips and almost unlimited connectivity. What has happened as a consequence is, unfortunately, this has led to vulnerabilities that are beginning to emerge, and we have to be worried about malicious activity that can happen as part of this overarching infrastructure. So that's kind of is the hypothesis that we are working with. Right? So I think that the issue of security and privacy has been addressed in there has been a lot of work over the last few decades. But the focus, however, has been on this approach of monitoring approach or the policing approach, where you basically, once you find an activity, you kind of try to weed it out. The problem that has become is, in the current context, the barriers to entry to do these bad things to your infrastructure have become much lower, and sending a single spam mail versus sending millions of spam mail has little marginal cost difference. Okay, so we really have to rethink our architectures and designs, and we have to start developing approaches that are more based not on monitoring approaches, but rather on preventive approaches. Okay, so that's kind of is my thesis statement, and with that we have to reevaluate the model that assumes the technology components are benign and passive. And we really need to start thinking about solutions that can withstand malicious activities in these infrastructures. So that's the okay. So the question is, can it be done? And my tongue-in-cheek, over the last decade, I think we all know there is at least one application we all are aware of that really deals with the issue of maliciousness or issue of untrusted infrastructure, and I hope you all can connect to it. And the one that comes to mind is the blockchain or Bitcoin. In the context of cryptocurrency, we know they're exactly dealing with the problem of maliciousness in the network infrastructure. So what I am going to do is, in the rest of this talk, I'm going to prove this hypothesis by more examples. But more seriously, what I'm trying to do is I'm trying to give you some solutions which I think is going to provoke more longer-term thinking in the direction of trying to incorporate trust in our infrastructures. Okay, so the plan is I'm going to talk about an application, in particular voice communication, where you want to hide who is talking to whom. And this is based on one of our papers which appeared in OSDI 21. And in the remaining time, I'm not going to go into details, but I'm going to at least formulate and give you an idea of the solutions for example, oblivious search from public repository, and the third one is going to be private query processing over public databases. So this is the plan. Okay, and the overarching theme in all this is we are going to assume that the underlying infrastructure is not trusted. Okay, so let's start with the first part. So we are really talking about voice communication, and the voice calls or voice protocols are ubiquitous, and they contain sensitive content. Fortunately, many of the voice call provisioning is based on end-to-end encryption, in the sense that your content is hidden using public-private key mechanisms in cryptography. So when you send some message, when you communicate with the receiver and send a message that can be easily encrypted, delivered to the receiver, and the receiver has all the necessary tools to be able to decrypt that message, and the receiver is the only one who knows about the content. Okay, so clearly this hides the content, and there are enough guarantees for content hiding. The question is, does it provide end-to-end encryption? Does end-to-end encryption solve all the problem? And what is not hidden from this communication mechanism is that you do not hide the identity of the endpoints of the participants. You do not hide the time at which the voice call was made. You do not hide the duration of the call. Essentially, all the metadata information is completely public, right? So I'm going to focus, although our solution addresses the time and duration issues, but I'm going to focus on the issue of hiding the privacy of participants. Okay, so the question is that really important? Well, I'm going to just put a couple of quotes from the reconnaissance and the intelligence community, these people, the big people, who say that metadata is important, and we can do a lot with this metadata. The second quote is a little bit darker. It says we can kill people based on the metadata. More importantly, what we have to realize is if our infrastructures are under surveillance by nation states or by other type of entities, you actually we have difficulty in ensuring some of the basics principles of democratic institutions can be sustained or not. So, for example, in the context of journalistic integrity, if you have a communication between a journalist and his information provider, this type of surveillance can actually identify or de-anonymize the person who the journalist is speaking to. So you really have to worry about what this metadata can do. Okay, so the question we have to ask is, can we make voice calls hiding metadata from a strong adversary? And in particular, what we want to be able to do is, since we are the database or the systems community, that we want to make this into a practical solution. And that's kind of is where we are going for. Okay, so So at an abstract level, there are two key challenges that we need to solve. One is we need to make the caller and the callee you need to unlink the connection between the caller and callee. So when Alice is speaking to Bob, what should happen is, for the rest of the world, it's okay for the world to know that Alice is talking to someone, but it should not be the case that they know exactly who she is talking to. Okay, so that's the first problem we had to solve. And the second problem is, since we are dealing with a latency-sensitive application, we don't have a huge amount of time to be able to do the processing and communication. So you need to do this as efficiently as possible. Typically, the latency budget in the context of voice communication is under it has to be sub-second. So it has to be within whatever you are doing, whatever hiding mechanisms you are doing, it should be done in a reasonable latency budget. So that's our second challenge, so as we are moving packets around, in order for the voice communication to be effective, it has to be done in a reasonable amount of time. Okay, so what I'm going to present is the solution overview relies on a communication architecture that leverages private information retrieval, and I'm going to give you all a quick tutorial on private information retrieval. And the second thing we do is the issue of scaling, so that you can support large number of users at the same time or concurrently. So I'm going to also be briefly talking about some of the solutions we have incorporated in the context of PIR, which is going to make this processing faster. Okay, so I'm going to give you just a minute overview of PIR, which I think has been around for almost 2 decades. And the basic idea of PIR is that you have a database content in terms of, let's say, n values that are indexed from 0 to n minus 1. And you have a user who wants to query the database, but the intent of the user is that the user does not want that the database provider to know exactly what the user is trying to observe or to query. All right. So basically, what you do is there is a mechanism by which you send your query or the index of the element that you are looking for in an encrypted form as a ciphertext, and then it's sent to the database provider. The database provider performs the operation and returns the result, which itself is an encoded form, and then the answer comes back to the user, and the user can decode the answer. Okay, so that's the idea of PIR. It's actually the nuances that there are 2 forms of PIR. One is called information theoretic PIR, and the other one is called computational PIR. I'm really focusing on computational PIR. Okay, so that's this is the backdrop that we are going to be using. So we are going to be relying on PIR, and in order to sort of solve the problem that we have at hand, we are going to use a classical mailbox type of a structure or mechanism at the server level, who's providing the voice service. Okay, so the idea would be is that the mailbox are owned by individuals, and there is the major distinction of this mailbox architecture is the classical mailbox architecture. So if you go to the post office, the mailbox is that essentially you own the mailbox, and when somebody sends some information to you, the information is deposited in the recipient's mailbox. Okay, so we are going to flip this around, and we are going to do the other way, where when a sender sends some information, the information gets deposited in the sender's mailbox. Okay, so that's the major distinction, and that's what's going to happen is when Alice wants to send her voice packet, let's say, what she does is she deposits the voice packet in her own mailbox, not to the recipient's mailbox. Okay, and when Alice and Bob are involved in the communication, what Bob does is uses a PIR and sends the query, and it basically, the query picks up the intended mailbox from where the message is going to be received. I hope everyone got this. Okay, so that is the basic architecture modification or component that we use, and with that, Alice can communicate with Bob, and later on, if Alice wants to communicate with somebody else, she's going to use the same mechanism by sending the packet on her own mailbox, and the intended recipient is going to pick it up from Alice's mailbox. Okay, so that's the basic idea. Okay, too much animation. All right, so this architecture is it might appear that you have to do the query for every voice packet. Actually, that's not the case. What you can do is you can install this query for the intended duration of the call, right? So when basically what happens is when Alice and Bob are connected, and I'm not bringing how they get connected. That's a separate phase or a dialing phase that I'm not getting into. But once the connection has been established, what Bob does is basically installs his query saying, I want to, for the next 5 minutes, I'm going to be talking to Alice, so I'm going to install my query to Alice's mailbox, and as packets arrive, those packets are delivered to Bob. Is that clear to everyone? Okay. All right, so the next step is, how do you scale this to large number of users, and in particular, how do you make sure the processing and the communication latencies can be done within the budget that we have? Okay, so when it comes to individual packet delivery, there is the issue of the overhead of sending the packet to the mailbox, processing the packet at the server, and then finally delivering the packet to the intended receiver. Okay, and what is used, so we are going to use something called the mechanism based on PIR. Over the last few years, there have been significant advances to make these schemes much faster. But typically, what these mechanisms do is they have a trade-off between the amount of processing you do and the size of the query and the response size, right? Okay, so we have, I'm going to just give you a very broad brush strokes of a mechanism called fast PIR, which is both faster than both XPIR and Seal PIR. Okay. All right, so the PIR, the computational PIR, is based on this idea of homomorphic encryptions, which some of you may already know, but I'm going to just quickly do an overview. And what homomorphic encryption does is it allows us to perform operations on the encrypted data itself, right? So you can add, so if you have encrypted data, you can perform addition, multiplication, and other operations. And historically, there were these operations have been around in a restricted sense. So there were partially homomorphic encryption, and a breakthrough happened in 2009 by Craig Gentry, where this was extended to all kind of operations. Okay, so it basically supports the fully homomorphic encryption, supports computations over arbitrary functions. Okay. The problem with fully homomorphic encryption is it is computationally extremely expensive. So it's really of theoretical interest, and they do have very high cost associated with it. Okay. So for example, for performing Boolean functions, which I'm going to come towards the end of my talk, it is extremely expensive and it is really not practical. But if you use fully homomorphic encryption in a restricted manner or judiciously kind of putting on the system's hat, then it can be made to work for practical systems. That's the idea. Okay, so and you know there was original homomorphic encryption, and there has been variants that have been developed. So I'm going to be talking about this BFP encryption without going into the details. The idea is as follows. So given a plain text, so for example, your voice message, what you do is you basically treat it as a coefficient of a polynomial of certain size, and in a, you know, of n coefficients, right? So you basically break the message up into these fixed size bits, and then you can treat it as a polynomial of a certain degree. And then what you do is you go through an encryption, and the encryption also is a polynomial of the same degree, but the difference is the coefficients become much larger, right? So they have a different size, and the idea is what you're doing is you're taking the plain text. Intuitively, all that is happening is basically you're taking the plain text and you're perturbing it, you're adding some noise factor into the original value, and you're basically putting it in a much larger field. That's the basic idea of homomorphic encryption, and that's how the sort of the encrypted data cannot be kind of decrypted by the other side, right? So the only person who has the enough information on the necessary keys, they can filter out the noise and decode the actual signal. Okay, so this is the idea of homomorphic encryption. So with that, I am going to just put some requirements as to what are the basic properties that are needed. So if you talk to your cryptography friends, they're going to say that in order for things to be secure, the degree of the polynomial has to be of a certain size, and typically it has to be 2 to the power 10 or more. Okay? The maximum value of Q is determined by the degree of the polynomial, and the maximum value of P, the plain text size, is dependent upon the size Q that you have chosen. Okay? And in general, the value of Q, the number of bits in the encrypted field, tends to be much larger than the plain text field. Okay? So just to make things more concrete, if you choose n to be 4,000, 4K, then the number of qubits, the number of bits in the encrypted field has to be somewhere close to 109 bits. And if Q is chosen to be 109 bits, then the P turns out to be somewhere around 19 bits. Okay? Okay, so why am I putting all this? Because basically we need to figure out what is the size of our ciphertext that we are going to be sending back and forth. Okay? So with that, if you work out the math, basically your ciphertext size, becomes almost like 64 kilobytes. All right? So just to summarize, to reduce the ciphertext size, you have to reduce, you have to have small n, but there is a limitation as to how small the n can be. To encode concisely in the plain text, you want P to be big enough, but then that also determines the size of the Q. Okay, so these are the constraints that we are working with, and let's just keep doing a little bit more of the math and see what happens. Okay, so with that overview behind us, let's see how the whole thing works. Okay, so the basic idea is you have a database of elements, some number of elements at the server. What you do is you perform a query. So although I'm showing you query in the clear, you have to remember these ones and zeros have been encrypted, so the server doesn't know what is 1 and what is 0. Okay, so this is just for us. We are sending a vector where we are interested in a particular entry, and that's set to 1 and everything else is set to the 0. And basically you perform a multiplication of these two elements, and then you get the answer, where you're going to get the database value corresponding to the bit that is set to 1. Okay, and in order to reduce the final result size, what we can do is we can do a component, we can take these ciphertext and we can perform the homomorphic encryption, which allows us to add things together. So we can add them all together and we send a single result back. Okay, is that everyone with me? Okay. So what are the challenges? Okay, so let's do the little bit of math. So basically, as you may have seen, the size of the query now has to be, ciphertext that you are sending for each element times the size of the database. So you have to send ones and zeros for every element that is there in the database, right? So let's assume we are supporting we are at the server, we are supporting up to 32,000 users, and the ciphertext size we had already said is 64K. Okay, with that, the size of the query becomes 2 gigabytes. All right. Well, that's okay. So that's one thing. The other thing is, we are going to, since we are a service provider, we are going to be most likely supporting simultaneous or concurrent conversations between many individuals and up to 32,000 users. So now we have the queries that have to be installed at the server is going to be 32,000 users, corresponding to the 32,000 users. So you have to multiply each query with every user that you have in the system, which becomes almost 64 terabytes. So immediately you will say, okay, this is not, this is all fine, but this is all theoretical. It is not going to work. And Mohan is already giggling. And so this is our first step, is how do we reduce the query size? Okay. So that's what I'm going to do. So just to backtrack a little bit, if you recall, I told you that I send this query vector which has values zeros and ones. But underneath this query vector, it has a structure which is broken up into these individual coefficients. All right. So remember, even though the ciphertext is shown as a degree and is a vector of a certain size, basically it has these coefficients. So we're going to leverage that. And what I'm going to do is, now I'm going to view my database not as ABCD, but in terms of those components. Okay. And I'm going to create cipher queries, which is going to be vectorized in using this information. And instead of sending this vector as ones and zeros, I'm going to send these encodings, which is going to correspond to these smaller vectorized elements. Okay. A little bit of details, just buy this for the time being. Okay. Now with that, what will happen is, we basically are going to perform the operations of these vectorized elements with the components in the database, and you're going to get the desired result, not in terms of the singleton A, but A1, A2, the corresponding coefficient. Okay? So with that, my query size is going to reduce to, from whatever it was 2 gigabytes, it gets reduced to about 0.5 megabytes. So the reduction we achieved by doing this encoding trick that I just described, it results from 3 order of magnitude reduction from 10 raised to power 9 to 10 raised to power 6. Okay, so now we are, we are kind of making things feasible in some sense. Okay. The problem is the result size is still too big because you have all these encrypted information that has to be sent back. Well, one thing you can do is you can basically combine these columns because only one column has a non-zero entries and everything else is 0. So you can just add them together and you can basically have a single band of those columns, right? It turns out even with that, our result size is quite a bit larger. In particular, if you work out the math, it is about 256 megabytes. Okay, so again, back to the drawing table and see if we can reduce the result size further, because this is still not, it's not practical. Okay, so here you can do a trick which is based on this notion of rotation. So in the context of homomorphic encryption, what you can do is you can perform an operation which is referred to as a rotation, which basically looks like this, where you rotate these elements by 1 position, 2 position, 3 position, and so on. And what you can do is you can rotate it, and then you can perform the addition of all these vectors, and you basically get a single vector corresponding to the result. Okay, and that basically results in one ciphertext which is about 64 kilobytes. Okay, so just to summarize, what we have done is we basically have dramatically reduced the size of the query and the size of the result, and the rotations are expensive both in terms of computation and the amount of noise that is added. In general, I think in the context of the setup we have, the rotation takes about 95% of the processing time. Okay, there are some more optimization you can do in terms of the rotation. So instead of doing the rotation in a linear manner, you can arrange them hierarchically like a tree of rotation, and you can do those tricks, which indeed we have done. But I'm not going to go into the details. I'm going to leave that. So just to summarize for this part, basically we reduce the query size to about 0.5 megabyte and the result size to about 64 kilobytes. Okay, and with that, all I'm going to say is that you can support sort of concurrent, right, sessions, synchronous round of communication, which are privacy preserving for 32,000 users with a latency budget of about 726 milliseconds, which is by the voice call standards is an acceptable standard. So if you want to scale it beyond 32,000, then this latency budget is not met. Okay. All right. So with that, I'm done with my teaser on the voice communications. I'm going to get to the next one, which is oblivious document retrieval. So that's the problem I'm going to do, and this is going to be even more dissatisfying in some sense because it's going to be shorter. But I'm going to give you just a broad overview as to what are the tricks and techniques that you have to involve in order to make these things feasible, right? Okay, so the setup is that you have a user who's accessing a public repository, so public repository of documents. For example, let's take Wikipedia in this context, and what he's concerned is that either a malicious actor on the service end or the service provider should not know exactly what documents he or she is trying to retrieve. Okay, And so the problem, the hypothesis of our problem statement is that can we allow kind of ranked document retrieval without having any trust in the service provider? Okay, so that's my thesis statement. And the question is, can't we do this using existing solutions? So one of the solutions that you might have heard about is this thing called oblivious RAM, a technique called oblivious RAM. Unfortunately, it's not suitable for public documents. So oblivious RAM can obviously provide you, privacy preserving access to your data, but the data should be owned by you. Private information retrieval does not work because the PIR requires you to know exactly the index of the document that you're searching for. Okay, so that doesn't work. There is something called PIR with keyword, which also doesn't work because it basically returns a single document and it doesn't return actually a ranked order of documents. Okay, so how can we do that? So one thing that happens is typically when we do our ranked document retrieval, it can be done in a single round. Okay, so it turns out if you want to do it using privacy preserving mechanism, you cannot do it, at least 2 rounds are needed. And you will see that we are reusing some of the PIR technique in the context of this solution also. Okay, so our problem is that you have these, the document repository, which has been, using TF-IDF mechanism. They have been ranked, arranged in terms of the keywords. And when a user performs a query asking for documents based on certain selected keywords, essentially what you want to do is you want to go and compute the score corresponding to these keywords for all the documents. Okay, well, it's kind of all you have to do is you have to do the PIR, but instead of doing the PIR against the document set, you're doing the PIR against the query, the keywords, right? So you basically will have a 1 and a 0 corresponding to the keywords you selected and unselected, and that's what you're going to do. You send that encrypted query, you perform the matrix vector multiplication, and what you will get is the encoded score, right? Now, in the classical case, when things are in the clear, the scores can be computed at the server to result in to rank order these scores, but here the server cannot rank order these scores. Okay, and that's the necessity for sending these scores back to the user. And these scores, the encoded scores, come back to the users. The user basically decrypts them, gets the rank order, and based on that selects some subset of documents and can perform the query. And I'm going to not go into that. But basically, at this step, you can leverage something called multi-retrieval PIR, which instead of selecting one index, you can select multiple index. So there are techniques that are already that are there that allows you to do that. Okay, so let's so I hope you got the idea. It turns out this 2-round protocol, if you go and implement it in its entirety, it takes an enormous amount of time. In particular, it has an overhead of about 100 seconds for a Wikipedia type of setup, right? So, and the time can be broken up into 2 parts: the query scoring part and the document retrieval part. Okay, so the challenge is that you're dealing with 5 million documents, and in the context of English, there are some 165,000 keywords, and basically it boils down to performing a matrix operation that involves 327 billion entries. Okay? And the question is, can we do better? I am not going to present the solutions, but what I am going to present is by leveraging some of the techniques of matrix multiplication and some clever system level solutions, what you can do is you can bring down this time from 100 seconds to about 3.5 seconds or about 4 seconds. Not acceptable as yet, but nevertheless a significant improvement in terms of doing ranked document retrieval in a privacy preserving manner. Okay, so I'm sorry if I'm going to leave you dissatisfied. There are some there is a Shoup-Halevi matrix multiplication mechanism that we use in order to make this feasible. Of course, you have to do some sort of partitioning and sharding and all those things, but that's kind of behind the scenes. Based on that, we are able to bring this time from 100 seconds to about 4 seconds. Okay, with that, before Chen throws me out of the podium, let me give you an overview of trying to do database operations on public repository. Okay, so what we have, my next problem that I'm working with is that I want to do a key-based retrieval from a key value store, and the problem is PIR does not support keyword-based retrieval. It supports if you know the index of the element that you have. Okay. So in the context of database queries, which is sort of attribute based querying, the notion of index is not available, and you want to be able to retrieve a specific, do a point query against a key value store. And the question is, how do you do that? Okay, and so the problem is you do not know the index of the key, because if you knew the index of the key, then you can just rely on the PIR to be able to do that. Okay, so there has been an extension of PIR to keyword PIRs, which dates back to 1998, and the basic idea was you arrange the keys in terms of a binary search tree, and essentially you do multiple step retrieval. So you do multiple steps and identify the index, and in the final step you go and retrieve the value associated with that index. Okay, so for variety of reasons, this is not an acceptable solution from a database point of view, because multi-step retrieval give rise to lots of problems. First, obviously we have an overhead of multiple steps, and you also, if your database content is getting updated while you are doing this multi-steps, that also causes problem. Okay, so the thesis statement that I'm working with is, can we retrieve the value in one round? Okay, so the problem we have is that it's a very elegant formulation. The abstraction is very nice. So you basically want to leverage PIR and homomorphic encryption, right? So conceptually, what you can do is you encode your keyword as a vector of the number of elements in your keyword store, key value store, and you basically replicate the keyword that you're looking as an entry in every element of this vector. Okay, I think you probably see where I'm going, and the cryptographers have said that you can perform operations, right? So you can do Boolean, you can do an equality check against this, and essentially what you do is you can convert your query vector by performing the equality check, and what you're going to get is a vector that will correspond to exactly the index that you're looking for, right? So you basically, when K1 and the encoded value of K2 is not equal to K1, then the Boolean value is set to 0, and when it is equal, then it is set to 1. I hope everyone sees that, right? So once you have that, the rest of the problem is easy, because then it is PIR against your value array, and you perform the value, the index, you do the PIR, and you can send the result back. Okay. So in some sense, our problem kind of reduces to doing this equality check, right? That's really what we should be able to. If we are able to solve this problem, then we are able to do the keyword retrieval using PIR. Okay. The problem is, again, theoretically, you can perform the equality check, but it is extremely expensive. Okay, so it is extremely expensive in the sense that it just does not scale. Okay, so that kind of, it's a bummer. What do we do? Well, you go back and look through things in the past and what has been done. So there is a result in number theory which goes back 1640. It's known as a Fermat's-Little theorem. Many of you probably know it, which says that if you have a number and you use an exponentiation and do a mod operation, then you can get a 1 or a 0 value depending upon this number. Okay, so just to summarize, what it says is, if you do an a raised to power the exponentiation and then take the mod, if a is non-zero, then the result is 1, and if a is equal to 0, then it will be 0. Okay, so we basically are going to use this technique, and in order to check the equality between the two keys, the function that we have to perform breaks down into these 3 steps. One is the subtraction. So you perform the subtraction, which is easy in fully homomorphic encryption. Next is exponentiation. Exponentiation is expensive, and it does create some noise problem, but nevertheless, it's much cheaper than performing the Boolean function, Boolean equality, and then taking the ones complement. Once again, this is also relatively simple. So just to give you the idea, I'm going to leave it at that, is you basically are looking for a key. So let's say you have a very simple key value store of 4 elements, 4 different keys, and you're looking for a key with the value 12. You perform the subtraction, which gives you the following result. Next, you perform the exponentiation using Little's theorem, and you are going to get, wherever there is a non-zero value, it's going to turn into a 1, and wherever there is a 0 value, meaning the match, where the match occurred, is going to be 0. And you actually want your query vector to be a complement of that, so you perform a subtraction, and that gives you the desired query vector. And after that, you can run with your PIR. Okay? So behind the scenes, of course, you have to overcome some of the systems issues and things like that. But nevertheless, at the high level, this is the solution framework. And with that, what I'm going to just leave you with is that we are able to do work with with 1 million documents. You come to about a second to a 2-second level of doing key point lookup against key value store. Okay, again, not satisfying, but you have to remember we are working in a very, very different sort of domain. You're moving from a clear domain to an encrypted domain, And these are the overheads that you have to work with. Okay, so with that, I think I'm almost towards I'm almost on my last slide. So obviously the overarching theme of some of the solutions that I've presented is based on this concern that we are dealing with untrusted infrastructures. There are malicious actors who are really engaged while we are performing the services and lookups and things like that. And user privacy has become a paramount concern. Okay. The solution framework, I think, it does require us to combine techniques from disparate areas. So we cannot just be focused on databases and systems and say that we are going to find solutions. We have to go out and look at what other communities have done, what advances that have happened in the last few years, and see if they can be made practical. I mean, I think if you think about it, you know, there has been this AI and ML revolution, and a lot of a big part of that revolution is that many of the techniques that existed for a long time got enabled because of the infrastructure advances that have been made. And I think to a certain extent, I think in the context of privacy, I think we are also at the same juncture. In order, we have to leverage, you know, large infrastructures, abundant resources, and, you know, advanced cryptography techniques to be able to solve these problems. And I should also add, it's not only databases, distributed systems, and algorithms, but and cryptography. I think scientific computing is also going to be very important in this context, because you often are dealing with large matrices and vectors and those type of operations. Okay, the parting thought I have is that, you know, one of the concerns I have is there is this community, there is this activity that is happening sort of outside academia, which is in the context of blockchains, and it is being projected as going to be the overarching solution for all our problems in the context of privacy and security. And I think to a large extent, I feel the academic community has ignored it, and I think we need to really engage and to find out what is happening, what is real, and what is not real. So with that, I'm going to stop, and I'm going to hand over to Chen to take any questions you may have. So I just want to once again say, if you really feel that solutions I presented kind of leave you dissatisfied, that's exactly was my intent. My intent was to bring this to you and tell you that this is what we can do, which is, you know, clearly is not acceptable from the type of solutions what Mohan would like to see, for example, here. But this is what we are working with. Okay, I'm going to stop.
Thank you, Divi. We have two microphones here. One is here. If you have questions, please line up. And we also have one microphone there in our with our volunteer. If you want to stay there, just raise your hand.
Okay, Murat, it's easy question, okay?
Okay. Actually, it's a hard one, I guess. We had last week NSF SATSI workshop, which is for those who doesn't know, it's a National Science Foundation that funds security and privacy research. And one of the themes that's coming up is there are all these cool privacy preserving solutions coming out, and we see two examples today, like privacy preserving voice call, documenting, and so on. But the adoption in industry, in practice, is very dissatisfying. And then, of course, there are many ideas on why that's the case. I would like to get your opinion. I mean, what will it take this to be adopted in a place where Mohan would like, let's say? Thank you.
So you know, I have to. So I'm an academic. I work on point solutions. I really don't, you know, coming up with the overarching solution. I think we are still. I think we are still far away from that, right? So, for example, I kind of told you during, you know, one of my presentation topic was privacy preserving database queries, right? But it's really not database query, it's point queries, which is really a small piece of the big puzzle, you know. So I have been, you know, once when homomorphic encryption, I became aware of homomorphic encryption, which was, I think, somewhere 2010 or 11, and I was all excited because I said, okay, finally we are going to do the, you know, solve the range query. If I can do kind of database querying, point queries, range queries, and perhaps aggregation queries on encrypted data, that is going to be, you know, a significant step ahead. Well, I think so range query still remains a challenge, right? Although CryptDB claimed, oh, we have done it all, but that was a false alarm. I don't think they really did it in a satisfying manner. More recently, I think in VLDB 23, there is an Alibaba group which is going to be reporting using homomorphic encryption for aggregation queries. But just to give you an idea as to the size of the data set they are talking about, is about an element with 8K entries. And the query processing, if I'm not wrong, takes 200 or 300 seconds. So really, I think what we need to do is we need to engage more with our friends in cryptography and make sure that they understand what database querying is, right? For a long time, the PIR community thought that doing the index retrieval is a database query. And this disconnect needs to be resolved in order to make progress. I think we still are far away from coming up with an overarching solution that is going to be solving the problem. But in the meantime, we have to keep pushing ahead. So that's my answer to your question. Jen.
Yeah, okay. Yeah, to show that you really get your purpose of the tutorial, so let me ask one question about your first problem. You say, well, we cannot identify the link between the caller and the receiver, right? But if both the caller and the receivers are in my network, so I can observe their activities. So these two.
Yeah. So I punted some of the details. The model that we have is there is a dialing phase and there is a communication phase. Yeah. Right. So the dialing phase sets up as to I'm going to talk to Yanis and Mohan is going to talk to Chen. That gets, so in some sense it's a synchronous rounds or something like that. So that's how it is. It's a limited solution. Yeah, it's not a complete solution. And then the synchronous communication round happens for a duration of 5 minutes, let's say, and everybody is going to be active. So even if I'm not talking, dummy packets are going to be sent on my behalf, and that's yes. We are in the blockchain world. Yeah. Yeah. So this is so I know, Mohan, you're not satisfied, but this is where the state of the art, at least from my point of view, that state of the art is. So Jen, it's a step in that direction, but it's not.
Yeah, exactly. Yeah. So my question, indeed, this leads to a question is that, well, when we talk about trust, how do we define, what's your opinion about how we can define trust, and also at maybe at different levels, right?
Yeah, you're catching me off guard. How do I define trust? So the idea of trust, from my point of view, is essentially I'm able to accomplish my task without the service. So these are all solutions which are service-based solutions, without the service provider knowing exactly what I'm doing. That's, I think, is how I'm defining trust. I think it's an operational definition, but that's what it is. Okay, Yanis.
Of your three things, I'm more fascinated by the first one. I mean, this reversal of the mailboxes, I think, is really.
Thank you.
Yeah, I really like that. But my question I've been trying to answer it myself, and I have failed as you were talking. So hopefully, yes, no. This is about the point tree queries, which is dissatisfying. I mean, we are used to other queries. Secure multi-party computation can deal with any computation, so to speak. So can you imagine having arbitrary SQL queries, or any queries for that matter, database queries, combined with your tricks and fine work on the point queries, so that we can, with secure multi-party computation, can be able to deal with more complex queries?
So, in all honesty, I think what I should say is that we have not looked at secure multi-party computation, and I think you're right. We should be able to bring it into the mix. We were trying to focus on a single server type of solution. Single server in the sense of, so that's why we were focusing on computational PIR. So the computational PIR, the advantage with CPIR is, you don't need multiple servers, whereas information theoretic, which I think gets into secure multi-party computation, requires multiple servers. So Yanis, just an honest answer would be, I don't know. I think you're right. There is scope for bringing that in and making it more effective, I think, in some sense. Thank you.
So yeah, from the beginning I was wondering, with the first problem you identified, how the heck does B know that A wants to
so
talk to
it? There are explicit protocols for doing what you are asking for, Mohan. They are referred to as dialing protocols. There is work by, if I'm not wrong, person at UPenn called Sebastian Angel. That group, his research group has a protocol which does this.
So you briefly said something like that at the beginning and said, I'm not going to discuss the details. But even then, I was like, how the heck does B know, A has sent one more message? Is it like polling versus interrupt?
No. So the way I admit I was trying to keep things at an abstract and simple level. So there are nuances that you have to worry about. So first of all, the solution is not completely asynchronous. Right. It is a synchronous solution. So you sort of go through everybody knows that we are now in the dialing phase, and then everybody knows that we are in the communication phase.
But even in the communication phase, are you expecting things to happen at a regular frequency?
Yeah.
Yeah, but that's not, again, very...
Yeah, I know. I'm not.
One person might speak for a while and then...
So the idea is everybody speaks for a fixed duration.
Okay, so all those...
So the time...
The moment kind of details were missing,
that's why I said that I'm going to be focusing on the privacy of the individual participants. The solution does, at least at a theoretical level, solves the problem of timing and duration, but the way it's being punted is it's because it's synchronous round.
But then Jian's thing was, hey, the fact that A and B are in the network itself could be revealing, right?
Yes, of course.
So it's not like the whole world's population is all there and you are somehow hiding the fact that it's only these two.
I'm going to admit all my limitations and drawbacks. Yes. More questions?
I have one question.
Don't be intimidated. I think I would appreciate questions from younger folks because.
I have one question.
Yeah, sure. You are younger.
Again, also about the first part of your three topics. I mean, you mentioned the concerns about trust. In fact, almost everybody in this room has more than one instant messenger on their cell phone. And even in our organization process for this conference, we heard different opinions about, oh, should I use WhatsApp, the Telegram, WeChat, Signal, the different instant messenger platforms. And for most people, even including people like here, we might not be familiar with what kind of a trust they can provide. I wonder whether you can give some comments about, for those kind of commonly used platforms, what kind of qualities of service or trust they can provide. I wonder whether you're familiar with this what they are doing here.
Above my pay grade.
Yeah. For example, like one of our volunteers said, "I'm sorry, I cannot get onto WhatsApp." He refused to get on WhatsApp.
I refuse to get on WhatsApp. I mean, he puts me there by me.
Yeah, I mean, Mohan is on every platform, right? So basically, he broadcasts the message across different platforms. But even for me, I have some concerns about some platforms. But for me, eventually, it's a trade-off between convenience versus privacy. And I had to give up my privacy in order to gain the convenience, efficiency. I wonder whether you can give some comments about the dilemma we are in here.
So the concerns are, I mean, these are genuine concerns because I think, if I'm not wrong, I'm not an expert, and Murat, you can help me here, but I think if I'm using, for example, I use iPhone, but if there is a federal mandate on Apple to provide information about me, I think Apple has to give everything that I have in the iCloud in some sense. And these are genuine concerns. Okay. Now, if I've done something criminal, then it's legitimate. But I think at the investigation level, the fact that everything that I have done is going to be investigated is very disconcerting. And that's, I think, that's one aspect. The other aspect is what we need to worry about, and is if you think about people, normal people in places like India or China, I mean, they're relying on this. Their life has become reliant on this device that they're carrying 24/7, and what's going on behind the scenes, they have no idea. I mean, we as experts don't know what's going on. Again, I think we should really be, I want to be cautious. I think I don't want to say that the sky is falling. I think we have really we have indeed collectively we have transformed the people in the lives of the people in the world. I mean, I think what you can watch now, on what people can create and innovate and things like that. We have enabled immense possibilities, but at the same time, I think we are in the phase that we also have to recognize we have created immense vulnerabilities, and I think I'm imploring all of you is really you have to start thinking the next phase, how to make these things more secure, more robust, better, and so on. So that's where I worry about these things.
Any other questions? If there's no other question, let's thank Divi for the wonderful talk. Thank you very much.
All right, thank you.